orbitals singly before pairing takes place. Electrons will enter into the degenerate orbital singly before pairing will take place. And quickly, Pauli exclusion principle is telling us that no two electrons in an atomic orbital can behave alike. That is to say that in an atomic orbitals, two electrons will enter into atomic orbitals that they cannot behave alike. That is what Hund's rule is explaining to us. Let us see the application of these rules. Let us see the application of these rules. S subshell has one energy level, or I'll call it one orbital, or one box, anyone you choose to. The important thing is for you to understand it. It has one energy level, it has one orbital. B subshell has three. D, 5. If you count it very clearly, you see. And F has how many? 7. And don't forget that each of these boxes, 2 electrons will occupy it. And that is in alignment with what you know before, that S subshell can take a maximum of 2 electrons. So if the 2 electrons in S subshell is accommodated in this orbital, 2 of it. Don't forget that if the 2 is occupying here, obeying Pauli exclusion principle, it means that the 2 will not behave alike. Either one is going up, the other one is going down. You will see the application. And look at where Hund's rule is applying. Degenerate orbitals like P, D, and F. It is telling us that before electrons will enter into these degenerate orbitals, that they will go there singly. That is, electron will enter here and here. If it remains, you can come back and start pair, or can come back and start pairing them. But before they should enter into this one by one, singly. If you make mistake of pairing them, you are disobeying Hund's rule. Let us see the application. Let us see examples of that. Let us consider those examples. They say that we should use Hund's rule and Pauli exclusion principle to write the electronic structures of the following. Oxygen. Atomic number is 8. You first of all use Avogadro principle to write it. That is SPDF notation. That is 1s2, 2s2, 2p4. If you check, if you count it, you get 8. Now, remember anywhere you see S has one boss. Look at it here. S has one boss. And 2 electrons are in S. The 2 electrons are represented this way. Have you seen it? You are weighing Pauli exclusion principle. One is going up, the other one is going down. There is no way you write it like this. If you write it this way, you are disobeying Pauli exclusion principle, or you decide to write it this way. If you watch, the 2 electrons are behaving alike, which is in contrast to what he proposed, that no 2 electrons in an atomic orbital can behave alike. There's no way they can behave in the same manner. It's either one is going up, the other one is going down, or the other one is going down, is going up. If it is like this one is totally wrong. It must be like this. Now, 2s. Anywhere you see S has one boss. Don't forget this note. S has one boss, and 2 electrons are entitled into that boss. And the 2 electrons must not behave alike. Don't forget. P, anywhere you see P has 3 bosses. It is orbital, but I'm just using boss so that you can understand what I'm saying. If you watch, this P that has 3 bosses, it has only 4 electrons. If you want to obey Hund's rule and pass your exam, let them enter into these orbitals one by one. If it remains, come back and pair. If you watch, I have 1, 2, 3. The electron is remaining how many? 1. So I can now come back this one and what? Pair it. But without obeying this law now, you see that some of the OBJ, some of the wire OBJ, you see something like this. They write it this way. After all, is it not the same 4 electrons occupying the orbitals? 1, 2, 3, 4. But it is wrong. Why? You have disobeyed Hund's rule. they must enter into that orbital one by one. If it remains, come back and pair. That is Hund's rule for you. If you write it this way, even though there are two electrons in the atomic orbitals, but how can you leave this one vacant? That is why it is necessary to put them singly. Let them occupy the orbitals one by one. If it remains, come back and pair. Some OBJ exam, even in this year's WAEC, I saw it in the exam. So, always remember Hund's rule. Let them occupy. I have told you it applies mostly in degenerate orbitals. What do I mean by degenerate orbital? Those shells, those subshells that has more than one orbital. Like this one, P has three, the other one five, and this one seven. This one seven, this one five, and the rest of them. So don't forget that this one is strong. This one is the way it's supposed to be. The other example is neon. Neon is 10, 1s2, 2s2. Okay? 2s2, even though we have not done this one, we will do it later. 2p6. If you count it now, it's 10. Now let us, anywhere you see s, you put one bus, and two electrons are there already. This is 2s. This is 2s. Look at the bus for 2s, or the orbital for 2s. This is now p. Anywhere you see p, it has three orbitals. They should enter that one by one. If it remains, come back and pair. I have represented three. It is remaining one, three. So I am pairing them now. And pairing them, I obey Pauli exclusive principle. They are not behaving alike, even in their atomic orbital. The next example is considering boron. Boron is 5. That is the atomic number of boron is 5. And as you know, 1s2, 2s2, 2p1. I've written it. If you count that now, it's 5. 2 plus 2, 4. 4 plus 1, 5. So, anyways, S has one bus. Don't ever forget that. And two electrons are occupying there. This is 1s. I'm going to 2s now. I'm going to present 2s. 2s, so far it is s. It has one bus. And two electrons are there. I'm now going to do P. Don't make that mistake of saying, what is the need of drawing three orbitals for P when only one electron is there? Don't make that mistake. Some of you will say, let me, is it not P that has one? Let me just put that one there. You have made a mistake. Because P has three orbitals. So I am putting that one electron here, leaving the two vacant. So P has three orbitals. You don't just say, is it because of one electron that I'll draw a whole lot of three orbitals? So please, you must put the three orbitals and represent the electron there. That is it for boron. Let's see carbon. Carbon is 6, 1s2, 2s2, 2p2. I think when you count the Z6, the S has one orbital. S has one orbital. This is for 1s, this is for 2s. Now 2p. You all know the same thing we did for boron, but this one has two electrons there. 1 and what? 2. Don't forget, let them occupy singly. Don't just go and carry this one and put here. You are failing it. Let them occupy 1, 1. If it remains, come back and pair. Don't forget. That is for calcium. And then let us check argon, which is the last one. On the example, argon is 18. 1s2, 2s2, 2p6. I think this is 10. 3s2, 3p6. Count it and see whether you see 18. 2 plus 2 is 4, 4 plus 6, 10, 12, and now 18. Anywhere you see S, as usual, put your one bus and represent number of electrons there. Which means we use this arrow to represent electron. These arrows inside that orbital. That is what we use to represent electron. 2s2, still have 2 electrons. Now 2p6. Don't forget that P has 3 orbitals. And you have 6 electrons there waiting for you. Waiting for you. Now 3s2 is there. This is 3s2. Now 3p6. 6 again. have three orbitals, put the electrons there. If you are watching how I am doing it, that is it. Pauli exclusive principle and the Hund's rule of maximum multiplicity. Maximum multiplicity. That is it. See you in the next video.